Welcome to Science Class Notes, and this is the A-level class notes on Arrhenius equation. Well, that's Arrhenius equation there. Looks very daunting, a bit scary, but we are going to try and make this a bit easier, a bit more user-friendly to help you guys out. Now, today's presentation or clip is divided into 7 parts, if you like. It's over to you. You can pause, you can fast forward to any point you like if you're more confident with this, or alternatively you can just stay with me all the way through. But first of all, we're going to start off with a bit of revision, going back over topics that you've covered in year 12. Let's have a look. So we start off with kinetics. Let's do a quick recap, mind map, if you like, or a spider diagram of topics in kinetics. So what was kinetics all about? Well, if we think right back to basics, kinetics is all about, if you think about the word kinetics, it's all about moving, and it's in fact collision theory. It's about collision theory where molecules or reactants need to move and collide. If they don't do that, then they won't react, and you won't have a chemical reaction. So collision theory was the first thing that you considered in kinetics, and there are factors which then affect chemical reactions. Things like temperature. Is the reaction endothermic or exothermic? What about in case of solids? Surface area is a significant factor. How about in liquids? Concentration, the amount of the substance. What about in gases? It's the pressure that governs the collision of particles. And also catalysts. Catalysts now lower this thing called activation energy. That allows a reaction to proceed, of course. Also in this topic, you looked at a statistical model created by Maxwell-Boltzmann, and it was called the Maxwell-Boltzmann distribution, where they looked at the average kinetic energy of particles and the kinetic energy of particles, which would lead to successful collisions and therefore reactions, having the right amount of activation energy as well. So this was a topic of kinetics that you did before. Now, kinetics is also linked to rates. Rates is a measure of kinetics, if you think about it. And it was all about, in this topic, you looked at the rate expression, if you recall, and this was determined experimentally. Also, from that, you worked out orders, rate orders with respect reactions in respect to concentration. From there you could work out the overall order. Also from the rate expression you could work out the constant K, and this is dependent on temperature. If you recall, for any given temperature it's got to be a constant temperature. K is constant. If you change temperature, you change K, which we'll look at shortly. And ultimately at the end of this, just to complete this, you looked at this thing called rate determining step as well. So this was a quick revision into the topics you've done. Let's have a quick look at this idea of K constant and being temperature dependent. If we have a look at some data, whilst temperatures increase, and you can see there's a relationship between rate and constant here. Have a look. You can pause the video, but if you look on, you can see as the temperature increases, the rate also increases. As the temperature, it's a very proportional relationship. But if you look at the data that's in front of you, if you plotted this, you could see that there's this positive correlation here. In fact, described as a hockey stick, one could argue. And you can see that there is a link between increasing temperature and the constant in any given chemical reactions. Now, let's have a look at this, linking rates and kinetics together. Okay, this idea. Well, it's the Arrhenius equation that does that, and in fact, the rate is governed by the K in this equation, which is proportional to the rate expression. Also, considering collision theory, it's this factor A. It's a constant which accounts for collisions between particles. And then you've got the Maxwell-Boltzmann distribution. Now, that in this Arrhenius equation is this expression. This tells us the tail end of the Maxwell-Boltzmann distribution, where particles have enough energy to react. Well, let's make this this equation a little bit more easier to understand. we know K is a rate constant. Now that's worked out from our rates topic, where you can look at, we experimentally change the concentration of substances and calculate the rate constant for any given reaction. A is the frequency factor. This takes into account the collisions and orientation. So that's your rate idea. This E is a bit like pi. It's not really that important just right now, so don't worry about it too much. And then you've got the gas constant, of course. That, remember, this comes in from your amounts of substance topics, where you are using the PV equation. And then you've got T, of course, that's the temperature, of course, in kelvins. And then you've got activation energy in joules per mole. Right, so here we go. This Arrhenius equation is really good and really useful because it helps us link all these concepts together. Because so far you've learned about changing concentrations, changing pressures, and how that changes rates of reaction, but we never considered activation energy and temperature. And it's this equation which allows us to link the rates of reactions with the activation energy and the temperature. So it's very, very useful in those terms. Right, okay, let's make this equation even more useful. Couple of ideas first. First of all, IN in this is natural logs, and on your calculator you can find that under, well, LI, LN. Looks a bit like an A, but it's there usually on most calculators to the right hand side. One rule to this: this natural log is opposite to E. It's all you've got to remember. Okay, and with that in mind, we can go ahead and have a look at this idea. So if we put this together, let's have a look. Let's have a go at this. So what I'm going to do then is I'm going to take the natural log of this equation then. So let's start off with the K side. If I take the natural log of K, that's going to be equal to the natural log of A, which then is going to be equal or added to the natural log of everything inside that bracket with E, because the activation energy and the gas constant with the temperature is to the power of E. Now, as we know from the rule, natural log is opposite to E, so that's very easy. We can get rid of that E straight away because they will simply just cancel out. We're left with then the natural log of K, which is equal to the natural log of A, and then we can bring down this expression from the power of E because we've cancelled it, and we can say this. Much more user-friendly now, much more nice to use. So the natural log of the rate is equal to the natural log of A minus the activation energy, EA, divided by the gas constant multiplied by temperature in Kelvin, of course. Right, so with this in mind, we've got a much more user-friendly equation now. Now, if you recall, I did say what happens is we can use this equation much more usefully if we're trying to calculate things like, let's say, activation energy or possibly a temperature of a reaction. And let's have a look. Let's have a go at deriving that. And this, in the exams, they can give you any type of equation. They give you the Arrhenius equation, which you need to come to this step by doing this calculation. So make sure you know how to do that. Also, they might give you this expression here, and then they might expect you to rearrange it to make something a subject. So, for example, the activation energy. So let's try and make activation energy the subject for this equation. And if that's what we're doing, we're trying to make EA the subject. It goes like this. It'll be the natural log of A minus the natural log of K, which is then equal to minus EA divided by RT. Okay, so if you remember this in the exam, it's really, really useful. Now we're trying to make EA the subject, and we're just going to put RT on the other side. So the thing to do here is just rearrange it. So R multiplied by T multiplied by then the natural log of A. I'm just going to put these into brackets just to make it a little bit more tidier. is equal to EA, or the minus of EA. And I'll come back to that later. So this is the way to derive this. We just rearrange this equation because activation energy has been divided by RT. What we can do is just multiply RT on this side, do the same on this side. We can remove the gas constant and temperature to the other side. Now, this is a much more useful equation because now we can work out activation energy. So that's really easy to do. It's pretty straightforward. Let's consider now possibly if an exam they could ask you to calculate maybe a temperature, or even R in that matter. But let's say if we're trying to calculate temperature here to make T the subject, very straightforward way of doing this would be, again, same as before. Let's get rid of, make it a bit more simpler for us. Let's put the natural log of A on the other side of the equation. So we've got natural log of A is then is subtracted from natural log of K. And then that equals what's remaining over here, which is minus activation energy divided by RT. Now, you could do this various ways, but one way which would be quite useful, which we'll look at later on, so we might as well have a go at doing this, is let's just separate the T out from this this side of the equation, just to make life a little bit easier and a little bit more friendlier, I guess. So what we could do is we can rewrite this side of the equation by just removing the T and leaving activation energy and gas constant together, dot, so it's times 1 over T, because something we've got this expression here, so it's 1 over T to put over here. So again, this side will just remain the same as the top line. Now this makes life a little bit easier. We can rearrange this equation to leave 1 over T as a subject, and let's remove R first. So just multiply this side of the equal sign by R and put R up here. So R multiplied by natural log of A minus, let's put this into brackets, makes life a little bit tidier, I guess, is equal to then EA, oops, we've got the minus EA, multiplied by the inverse of T. Now, again, we can quite easily just move the EA over to leave 1 over T over here by just dividing everything by EA. So if we divide both sides of the equal sign by EA, activation energy, we're left with R times natural log minus the natural log of K, the rate, and EA can come down here, and we're left with 1 over T. Now, 1 over T is not as useful as it could be. So what we could do is just flip this to make T on the top line. If we flip this side, then we flip this equation, of course. So then we have a much more useful equation for calculate this. I'm afraid I've run out of space here, so I'm going to have to make a little bit more space, get rid of some of this. And okay, let's do this now. And then what we could do is rewrite this equation in making T the subject then. So T is then equal to E8, all is going to be divided by the gas constant, let's just say, times the natural log of A minus the natural log of K. Much more user-friendly, much more nicely. So two ways you could two things you can do from this, for instance, make subjects out of these. Now, as I say, in the exams, they will expect you to be able to do that in any given context. So make sure you can. Here you go. Let's have a look at an exam question then. Let's practice an exam question. Here's a question I found. That was in 2 parts. There's a part A and a part B. I didn't bother with the part A because that was just calculating the rate. And that's fairly straightforward. So calculating from part A, we had to do the rate. Now, the idea of this equation. Now, remember the idea of this whole presentation or this whole clip is for you to pause the video, have a go for yourself if you wish, or just follow on as you go along. So let's have a look. So they gave an equation for a rearranged equation for Arrhenius as this. And what you had to do then was, in the end, calculate the activation energy. They've given certain values, which we'll go through in a minute, but let's have a quick look at this idea of, again, applying the idea of rearranging this and making, in this case, activation energy the subject. Okay, remember you can pause at any point as you wish, and you can have a go at this yourself. Okay, so let's have a go at rearranging this. So as before, let's move the natural log of a to the other side, makes life a little bit easier. And what we end up with then is the expression starting off as natural log of a, there it is, minus the natural log of k, which is then equal to divided by RT. There we go. So from this position, from this area, what we could do then is we can obviously we want to make EA the subject. We can remove RT by just multiplying both sides of the equation. So R times T times, I'll put this in brackets again just to make it a little bit more neater, which will then equal to minus activation energy. Okay, so this was the derivation part of this equation. Let's have a look at the numbers now. Here we go. Got some numbers for you. Right, we have to be a bit careful of what we're using here. So what I'm going to do is I'm going to go through some of the numbers very quickly. So let's, if you read the question through, use the equation and your answer from part A, and I've put part A down here, the correct answer. There was an option to, if you couldn't calculate part A, to use a number that they'd given, but I've taken that out because we're going to assume that you got that right. So part A, to calculate the value in kilojoules per mole for the activation energy. For this reaction, we're going to calculate the activation energy at the temperature of 25 degrees centigrade. Now, temperature 25 degrees is room temperature, so at room temperature, without using a water bath or a Bunsen burner or anything like that, what's the feasibility, what's the activation energy for this reaction? So let's have a look. First thing to do, and most important thing to do, is let's get rid of this degrees centigrade and put it into the right units of Kelvin. All we need to do is add this number to 273 to get Kelvin. So that works out to 298 then Kelvin. Okay. Now let's have a look. So for the other information they've given us the natural log of A. There it is. So that's fine. They've given us the gas constant. So that's fine. Now they've also given us the rate, or the rate we calculate from part A. There it is. And we know it's rate because look, if we look here, it says rate, but also look at the units, and that's very important. Now this is not very useful to us. We need for rate in the Arrhenius equation. It's actually K, isn't it? If you recall, K is proportional to the rate of the reaction. So I won't do that just yet because I want to show you something as we go through. So let's start putting the numbers in and working our way through. So activation energy is then equal to the natural log of 8, which is 16.9. That's the value they already given us, calculated for us very kindly, I guess. And we're subtracting it from the natural log K. Now here, what you need to do is take your calculator. I'm doing the same as well, and you press the natural log button, okay, which is LN on the far right hand side of your calculator. Usually, when you press that button, you get on your screen an open bracket. Into that bracket, type in the number. Okay, which is 2.8 times 10 to the minus 2, and close the bracket, of course, just for to make sense. You get a number then, and the number is minus 3.576, let's just say. Now, this is the point. Let's carry on and just add some more numbers to this. Multiplied by the gas constant, they've given us that as 8.31 times our temperature, which is 298 in Kelvin. Right, got all the numbers in. Now, this is the good thing. On my calculator, I've already worked out the natural log of K. It's already in my calculator. So this is where rounding off can be a bit confusing. Best thing to do is leave that number on your calculator. Zero your calculator, then put in 16.9, subtract it from the answer, the answer button, if you press that, it'll give you a more accurate number, which you can apply to your answer. Just for the sake of me writing something, and again, for you to write something, you can just round it off here. It's fine. You don't have to write the full number in. But then once I've calculated this, this works as 20 point. We'll use 20.476 multiplied by 8.31 times 2.98. Now, if you show this level of working out in your exam, then you can see where you've gone wrong if you're checking your work through, and the examiner can see where we're going with this. And once again, since I've got this number on my calculator, and I've rounded off on the paper on the screen, but on my calculator it's the full number. All I need to do is multiply this number by 8.31, multiply that by 298. I end up with an answer then of 50705, and I'm just going to say, just for the sake of it, I'm going to say 0.2. Will do. Now this is the activation energy, and that's in joules per mole. Now if you look at the question carefully, they want this in kilojoules per mole. So you simply just take this number, divide it by 1,000, which comes in at 50. Let's just round off 50.7 kilojoules per mole. And just to round things off, and just a round number, we can express activation energies as a round number of 51. Why did I write 50? I don't know. Let's just get rid of it. And it's 51 kilojoules. Oops, kilojoules per mole. And that's your answer, which you insert on the line. And that's it. Job done. And that's 4 marks straight away. Thank you very much. Fairly straightforward with a little bit of work, not too much, mind you. So it's not too taxing to score those 4 marks. And remember, 4 marks is still a grade boundary. Now we're over to another way we can use Arrhenius equations and Arrhenius plots. So using very straightforward Arrhenius equations to plot data on a graph, and they always come out as straight line graphs, and we can of course then apply that GCSE concept that you learnt about straight line graphs and that equation, which is the y is equal to mx plus c equation. But just before I do that, in an exam, again, they might give you this form of the Arrhenius equation. To make life a little bit easy for yourself, I suggest you just take out that t. So if you, again, just remove the t away from this, it will make life a little bit easier, because if I remove the t like we did before, if you put this equation like this, it's much more easier to compare to your ymx. Oops, it should be, what am I writing, an x or an m? I'm not sure. Let's write an m for the gradient, of course, and x for the intercept, plus then c for the intercept. So x is the x value. Now, just to make comparing this equation to this equation, if we just slightly rearrange this just to make it a little bit more user friendly, it's the intercept minus the gradient times the x value. And now if you look, k is the rate constant, and it's proportional to the rate. So in an experiment, I can measure the rate by changing the concentration. Also, I can change the temperature of an equation. So now this becomes a lot more user-friendly. And I can then, once I've got a series of data for a series of experiments, I can plot this onto a graph. Okay, so it makes life easier on this. If you do need to stop this video and go back over this so you understand this, it's fine. So we can take this is going to be on the x-axis, and the natural log of of the rate is going to be the y-axis, and we can see from this that the intercept will be this constant here. There you go, constant. And then this expression here, the activation energy divided by the rate constant, is the gradient of our straight line graph. Here's some data I've got here, and now we're going to use Excel. It's a good practice to use Excel when you go off to universities, etc., onto your degree courses, or even any work that you go onto. Excel is used more and more these days as opposed to using tables or drawing tables. So it's very useful using Excel, the software for Excel, to do this. If you open now, this is again something else. Now in an exam, you will have a table like this where they'll give you data and blanks which you need to fill in and calculate for yourselves. So make sure you know how to do this. I'm going to demonstrate this on Excel, and there is a component of your specification that needs you to use software externally. So it's worthwhile learning about this now. It's really useful and we can do this. And programming cells, I'll show you a very simple way of doing it, and really, really helpful, even when you're at this level as well, if you want to plot data, etc. Usually your practical endorsements will require you to hand draw these things, but you can also hand it in as a printout, as well as your as hand-drawn graphs, etc., etc. So we've got 3 more columns thereafter. We've got temperature in Kelvin, we've got 1 over T, and then we've got the natural log of K. And here we got T here at degrees centigrade and K here. So first thing we need to do is, let's look at this column here. We're going to convert temperature into Kelvin. Very easily done. Equals, open bracket. If you click on this cell here, which contains the number 5, add 273, close bracket, hit that tick button, and it automatically calculates this value in Kelvin for you. Drag down straight through the columns and it'll convert all of these numbers into Kelvin for you. Then you've got this as well. You've got to take now the reciprocal of the temperature, and again, same idea, equals, open bracket, 1 divided by this cell here, that's where your number is, close bracket, click on that X and drag down, calculated for you. And here we go, same thing here. Now this time we've done with the temperature, we're going to look at K. So again, what you type in is equals. Here, bit of mathematics, I guess, which if you look on the maths and formulations of this, you work out that natural logs is capital L and capital N, and all you need to do there as well is again plant the cell into this. And where are we? We are looking for K, and K is over here. Let's close the bracket and then click on the tick again, and there we are, drag down, and it works these numbers out for us nicely. Another useful tool for using Excel is to actually plot graphs. If I highlight all these cells and I go over to insert, go over to scatter diagram, and let's put a scatter on this, it automatically plots this for you. It's very useful. In my time at research, I use this a lot of this Excel spreadsheets to store data and then to make lots and lots of graphs from it. Now, there's no line. There's the plots, nicely plotted out for us, all done by the computer. All we need to do now is, if you right click on one of the points, it highlights all the points. Go down to add trend line to this. It gives you that straight line then. Also, if you go down to the bottom of this trend line, it says here, display equation on chart. There we go. Let's close this down. This now is the plotted data that you've put into the cells in Excel. It becomes very useful. You can do all sorts of things from here. You can put titles in and label the axes, etc., by just pressing the plus button here. And if you put that in, you can do that here as well. And fantastic, you can copy and paste this, and you can export this to a Word document or even a PowerPoint, etc., which is what I've done. And I have put the curve in like this. Now, after plotting the data, activation energy can be calculated. Now, of course, in the exam, you have to take the gradient. You have to calculate the gradient using a ruler. And the bigger the gradient, the more accurate you use. So in an exam, when you've got that graph paper, you've plotted this, use a ruler and a nice big triangle underneath that line to work out your gradient. Here, we've done it electronically, so it's a lot easier. And here it is down here. So the gradient of this slope is a minus number because it's a negative gradient. Here it is. Okay, so we've got that. That's pretty useful. From here, let's go on to the next part. So here we have in the exam, I guess, you may have worked out the gradient from your graph, but that is not the activation energy. Because that gradient is equal to the negative of activation energy divided by the gas constant, we need to remove the gas constant. So obviously, pause the video at any point you wish, but I'm going to go through it here. So we rearrange this equation to make EA the subject. R we know is 8.31. Once we do the calculating, we get a negative number. Of course, the negative on either side of the equal sign will cancel each other out. And another noteworthy point is activation energy is going to be a positive value, because if you think about those graphs that involve activation energy in kinetics, if you look at it, the activation energy is always a higher amount of energy. It's always an endothermic value, so it's going to be a positive number. Okay, remember this is in joules per mole, and it'll be nice to express as kilojoules per mole, because it's nicer to look at these numbers. So divide by 1,000, and then just round off to a whole number, 36 kilojoules per mole. So that's one way of doing this. Now, here's a great opportunity to do some exam practice here. Using this equation and starting from what you've learned throughout this, you could always pause the video and go ahead, and for each temperature, you could try and work out the activation energy. Okay, and one way you could do this is obviously by rearranging that equation, or of course by plotting these things, which we've done. And let's see if this is true. Let's see if that computer generated gradient does equal to this idea. So over to you. You can pause the video, go from the top, rearrange that equation to make E the subject if you wish, or we can just go from wherever you like to go from. So let's I'm gonna go through a quick calculation with you before we just finish up. So let's have a look at this then. So we've got there's our data. Let's pick right, we've got the intercept here. They're giving it to us as 14.3. Now I took that off the graph, so that was already there. Now if we rearrange this equation, make E the activation energy, the subject, and remember that's the natural log of A subtracted by natural log of K, which is equal to R times T. There we are. We'll take the numbers, and I'm going to, let's just start off with the first row. It's not a problem. We can add to this. So we know it's 14.3 minus. Now here we go. There's the natural log already calculated from us, so we don't need to use our calculators here. But if you recall, it's wise to maybe use this practice and go ahead and do this. So into my calculator, I'm going to press the natural log button. I'm going to add 0.326, close, and I'm going to get an awfully long number. But just because I'm writing this here, I'm just going to write down the rounded off number. But on my calculator, remember, I have got the full number. So in your exam, make sure you use the full number. Don't round off too soon. This is the wrong time to round off right at the end. Multiply it by the gas constant, multiply it by the temperature, and the temperature here is this number here. So 278. And remember, in your calculator, once you zero your calculator, you just type in 14.3 minus your answer button, and you've got the number there. I've got 15.420859579. All I'm going to do to that number is I'm going to multiply it by the gas constant, And then I'm going to multiply that number by temperature in Kelvin. I then get an answer of 35624. I'm just going to round it off the first decimal place, which is then 5. Let's just round it off to 5. 0. Okay, now, of course, this is in joules per mole. Looks very untidy, I guess. So we can change it into kilojoules per mole. So divide by 1,000. There we go. 35.6. Let's round it off there. And then if we round this off all together, and this is kilojoules per mole, of course, 36 kilojoules per mole. And that meets our gradient, of course, as well, which was 36 kilojoules per mole. So that works as well. So that's proven. You can practice this by, again, going through all the motions from the Arrhenius equation, which is at the top of the screen there, through each and every one of these, and practice calculating the various things. You can rearrange it, practice calculating the temperature as well. Thank you for your attention here. I hope I've helped you. If I have, please let your friends know if they need help with making Arrhenius equation a bit more easier to understand. Please also remember to like and subscribe as well. Thank you.